Chapter 5, Section 5.6, Trends in Periodic Properties. This section is huge. Honestly, in a lot of textbooks, this is its own chapter. Couldn't get my keyboard off there. This is a very big section, okay? And it's really, really important that you know this information. Not only that, that you phrase it properly. All right? So I'm going to spend some time on that and make sure that you work on this. This section on mastering on this will be pretty helpful too. All right? So what this is all going to talk about are trends or patterns in the periodic properties. So in other words, how the atoms behave, their shape, stuff like that. So as I told you, the periodic table is critically important, and this sort of gets into that. First, let me introduce you to the idea of valence electrons. So valence electrons are the electrons that are located on the outermost S and P sublevels. Okay, so this periodic table is showing you only the outermost S and P. So let's take a look at something like fluorine. Fluorine's electron configuration we learned is 1s2, 2s2, 2p5. So how many valence electrons does it have? Well, it's the outermost S and P, which are right there. So it has 7 valence electrons. Okay. If we look at something like chlorine, moving on down, chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So we're looking at the outermost S and P. That's those guys right there. So how many valence where'd you go? How many valence electrons does chlorine have? Chlorine has 7 valence electrons. Guess how many bromine has? 7. So let's go back and grab our trusty old periodic table. Let's grab this one. I didn't write on this one all that much. So let's copy that. Let's get a new page. So we get another periodic table. All right. So valence electrons. Let's talk about them. Group 1 is going to have 1 valence electron. So this is the number of valence electrons. Group 2 is going to have 2 valence electrons. Skip the D block. They're going to have 3 valence electrons, 4, 5, 6, 7, and 8. Now, what's important is that the number of shielding electrons. So what does that mean, shielding electrons? Well, the shielding electrons are all the inside electrons. So the number of shielding electrons increases, right? So if I'm going to write the number of shielding electrons here, it would be there are no shielding electrons here. There are 2 shielding electrons there. There are 10 shielding electrons, then 18, then 36, then 54, and then 86. Well, I usually don't get that far. But that's how many shielding electrons. And again, those are the inside electrons. Let me show you with neon here. All right, we're going to go back to the Bohr model. So here's the Bohr model. It's got a nucleus. The first energy level, which is 1s, can only take 2 electrons. So there's 1, 2. Now the second energy level, I'm going to do this in black. The second energy level for neon has 2 in the S. So there's 1, 2, and then 6 in the P. 3, 4, 5, 6, 7, 8. Okay, now these in the black, those are the valence electrons. In the red, those are the shielding electrons. So it's basically all the electrons that are not the valence electrons. Okay? So that's valence electrons. Let's go back to the notes. Here, let me title this. Valence electrons. What's going on? Just got a visitor, security guard. I may be kicked out. All right. So let's go. What are we doing here? Where are we at? Periodic table, periodic trends. Where'd you go? Section 5.6. Ahoy. Oh, missed it. Okay, so we talked about the valence electrons. Keep in mind the valence electrons. So up and down the group, same number of valence electrons. Okay? Number of valence electrons does not change. The D block, it varies, and we'll talk about that more once you get into AP. So we can show valence electrons as dot symbols, and we'll use this more in Chapter 10. But basically, think of the atom as the being in a box. Okay, so let's do nitrogen. Nitrogen is a good one. Okay, so here's nitrogen, and how many valence electrons does nitrogen have? Pause the video and check it out. It has 5 valence electrons. Okay, so what we do is imagine that there's a box around nitrogen. You don't actually draw a box, and then you can put 1 dot on each side, and then go back and give everybody a second dot. So for nitrogen, it's going to be 1 dot, 2 dots, 3 dots, 4 dots, 5 dots. Does it matter where that second dot goes? No, it does not. It doesn't matter at all. Okay? So you can see some of those dot symbols. Again, we'll use this more in Chapter 10, but they introduce it here, which is fine. Okay? Okay, let's talk about atomic size or atomic radius. Now, what we're talking about is the distance from the nucleus to the very outermost electron. Okay? So, again, there are the trends, and then there are the reasons for the trend. The trend is important. You need to know it, but you need to know the reason for the trend more importantly. Okay? Now, I'm going to introduce you into a way to answer questions. Whenever you answer questions, especially anything that says explain or justify, those are 2 different terms. To explain basically means to give a definition of, and to justify basically means use data or something in the question to answer the question. Okay, and we'll get into that more in AP. But what you have to do is you have to, let me write this down for you. We're going to write this down. I'm just going to write it down right here. First, you have to answer the question. So this is a way to answer all of our essay questions. So answer the question. Answer the justice question. Explain your answer. Explain your explanation. Okay? So keep that in mind. Answer the question, explain your answer, explain your explanation. Because typically what happens is that students don't give enough information with the question, and so they don't fully explain it. And that's what I'm looking for, is a full explanation. Alright, so let's get back to this atomic size. So remember, it's the distance from the nucleus to the outermost electron of that atom. Okay? We can also measure by stacking atoms together. So here's an atom, and then here's an atom, here's a nucleus, here's a nucleus. Here's an electron, here's the other electron. So what we do is we measure the distance between the nucleus and then divide it in half. Okay, that's another way to measure it. All right, so for a group, the atomic size increases going from top to bottom of a group. Let me show you what that means here. All right, so here's our periodic table. That means that hydrogen is small, francium is big. So the atomic size increases as you go down a group. Now we're going to come back and explain that in a second. Let's skip to right here, and we'll say the atomic size of representative elements decreases from left to right. Now what that means, go back to your periodic table, what that means is, here's helium, or no, let's use lithium. Let's use lithium instead because it's a better example. Here's lithium. Make it kind of big like that. And then as we move over here, it gets smaller too. Here's neon. Neon is much smaller than lithium. Why? Alright, so let's now get into the why. First, let's talk about from left to right, so across the period, why does the atom get smaller? Okay, you guys know about Coulomb's law. So Coulomb's law says there's this force of attraction between these 2 charges, Q1 and Q2, and it varies or it changes according to the distance squared, right? So as this distance gets bigger, this force gets smaller significantly, right? And we can say vice versa. As this distance gets smaller, this force gets bigger, right? Significantly. So what's happening? Well, here's lithium, right? So lithium has the, here's the nucleus. I'm going to show it as a positive. Here's the nucleus. Here's the first energy level. First energy level has 1, 2 electrons, right? The second energy level then has 1 electron on the outside. But what's important is that that lithium has 3 protons attracting electrons, okay? Now, they say that the shielding electrons, so there they are, the shielding electrons, what do? They shield the atom, or they shield the valence electrons from the nucleus. Okay? So that means, what that means is, those 3 protons are being shielded by 2 electrons. Okay? Now, there's something called Z effective. Okay? And you guys should know that Z is the symbol for the proton. So what this basically is this is the effectiveness of the protons, right? So the Z effective for this, the simple Z effective, is equal to 1. Okay, so that's lithium. Let's look at beryllium. Okay, beryllium now. Here's the nucleus. It has 2 electrons, shielding, and now it has 2 electrons on the outside. Now, you know, it's do you really want to think of it as 2 electrons on the outside? No, sort of think of it as 1 electron out there. But the big thing, it has 4 protons, right? So this was lithium, this is beryllium, right? So it's got 4 protons. How many shielding electrons does it have? It's got 2 shielding electrons. Where'd you go? So that means its Z effective is 2. It's twice as effective. So what happens is these protons, there's more protons, will pull in the electrons with a greater force of attraction. Let's skip over to boron. See what it does. Here's the nucleus, 2 electrons, right? It's got 3 electrons on the outside. Think of it as 1, really. So what do we have? We've got 5 protons, because now it has 5 protons. There are only 2 electrons that are shielding. It has a Z effective of 3. No units on Z effective, it's just a number. But what that tells you, that boron is even more effective at pulling in those electrons. So it gets smaller from left to right. Metals are bigger than nonmetals. And then even within nonmetals, they vary in size. So even in here, so like carbon is much larger than neon. Phosphorus is larger than argon. Selenium is larger than krypton. Okay? So from left to right, the atom gets smaller. Why does the atom get smaller? Because the protons are effectively stronger. Let's just jot this down. So it's sort of given to us right here. The attractive forces of the protons in the nucleus increase from left to right. More protons being added. And let's add something to that here. Same number of shielding electrons. This increase in force of attraction causes the valence electrons to be pulled in closer and closer, thus resulting in a smaller atomic radius from left to right. Now, let's go back up here from top to bottom. The atomic size increases. Why does the atomic size increase? Because we are putting electrons into higher and higher energy levels. Okay? So the atomic size increases because the electrons are placed into higher energy levels. Remember, more energy means further away from the nucleus. So here's the nucleus, here's the nucleus, here's the nucleus. So we can see that that electron is in fact getting further away. Now, what does that mean for the force of attraction? Right? What does that mean for the force of attraction? That means that that smaller atom has a big force of attraction for the electron. That means, here's the middlest atom, I'm just going to draw that. That means that this big atom has a small force of attraction. Okay, so keep that in mind as we go along here. Now, the most important periodic trend to know is the atomic radius. Everything else is explained because of atomic radius. And you'll see that as we go along here. Right? So let's move on. Oh, here's a picture. So you can see left to right. Gets smaller. Top to bottom gets bigger. But again, knowing the reason why is more important. Okay? Alright, let's talk about the next trend. This is ionization energy. Ionization energy is the energy required to remove a valence electron. Okay? And energy is required because of that force of attraction that we just talked about. So the force of attraction between the protons and the valence electrons. So here's the rule. The smaller the atom, the greater the force of attraction. Okay? The greater the force of attraction, the greater the ionization energy. Okay? So from top to bottom, ionization energy decreases. Why? Well, because the atom's getting bigger. Since the atom's getting bigger, the electron is getting further and further away from the nucleus. So you can see that here, lithium, sodium, potassium, bigger distance, right? Think back to Coulomb's law. Q1, Q2, we're talking about electron and proton here, so opposite charges, so they attract. R squared, as this distance gets bigger, this force of attraction gets smaller. So that's why it takes less energy to remove the electron as you go down. Left to right, ionization increases. Why? Because the atom gets smaller. Remember, atomic rate is very, very important. So as that atom gets smaller, the force gets bigger. Metallic character, I don't know. More and more people are starting to make it important. Whatever. Let's look at a periodic table, and we'll talk about metallic character. Okay. So what I always like to look at is look at this column right here, the carbon group. Okay. Carbon. That's orange, man. I don't like that very much. Let's zoom. Okay. So we know that carbon is a nonmetal, right? So carbon's a nonmetal. Silicon is a metalloid. Germanium is a metalloid. Tin is a metal. Lead is a metal, and whatever that is, that's also a metal. Okay? So metallic character from top to bottom increases. Metallic character increases from top to bottom. From left to right, metallic character decreases. Why? Lithium's a metal. Neon is a nonmetal. Okay? Now, what does that mean? Well, metals tend to lose electrons easily. Nonmetals tend to gain electrons easily. And that's the big thing for metallic character. Zooming along, cause can't find my note. There we go. Metallic character. Okay. Big one to remember, these two. Valence electrons, very important, but again, it's just 1 through 8. Atomic size and in ionization energy, critical, especially in all of AP and then all of your upper sciences as well. So very important. See ya.